Is it? Yeah, it is working. Yeah, can you hear me? Can you? Can you hear me now?
Hello, everybody. Uh, we will be starting Professor Valluri's talk in just a few more minutes. He's here. So please bear with us for the slight delay. Thank you. So good afternoon once again, everybody, and very hearty welcome to today's seminar. This is in continuation of the CAMOST-G20-S20 Consortium seminar series. And we are well into the series now. Now, one question which might have occurred to your mind is, what is the nature of interaction between gravitational fields and electromagnetic fields? And okay, does a graviton and photon, do they interact? And if they do so, then how do they do? Some other questions which may come to your mind is how to solve one-dimensional problems in quantum mechanics. You solve the Schrodinger equation for a finite square well and use the equation of continuity, apply boundary conditions, and then you run into a problem because you hit transcendental functions. So books like Schiff's quantum mechanics or Merzbacher's quantum mechanics will tell you that there are no analytical solutions, and the only way you can get the solutions is by using either numerical methods or graphical methods. But then there are ways of getting very beautiful solutions using complex functions. And in particular, a function which is very powerful in this respect is the Lambert W function. So we have an expert on things like the interaction between electromagnetic fields, gravitation fields, the Lambert W functions. Very fortunate to have Professor Sriram Valluri with us from the University of Western Ontario. He studied earlier at IIT Kanpur, subsequently got his PhD in Canada. He's a close friend, so it's very difficult for me to introduce you, Ram, because knowing you, there is so much that I can tell them about you, your background, your interests, and your expertise, because Professor Valluri has worked in very many domains, very rich contributions to quantum scattering theory, and then applications of mathematical physics in a large number of different domains. And to IIT Tirupati, he is a tremendous asset. I would like to mention that there are 6 undergraduate students at IIT Tirupati who have already published papers with Professor Valluri in some major journals. So he has been involved in mentoring our students, and that is the reason I wanted all our MSc students also to interact with him. Yashraj is here. He is the latest batch of students who will be working with Professor Valluri. There are 2 students from ICER also who have worked with Professor Valluri in published papers. Professor Valluri also worked on his work on gravitational waves is of interest to the LIGO investigation in India. He's working closely with Indian physicists on the LIGO project. Some of his work has been at least impacted by Abdus Salam at the International Center for Theoretical Physics. So today he will be talking to us about a very exciting topic. So let me welcome Professor Valluri. Thank you very much.
Thank you. Thank you, Pranava, for such a kind introduction. I'll try my best to live up to such a nice introduction that you have given me. And the topic I'm going to speak about today, is there a laser pointer? Okay, sure. Thank you. The topic I'm going to speak today is one that has interested me for more than 2 decades, and that is pulsars. I'll show you shortly some slides on pulsars, what exactly are pulsars, and how, for example, pulsars can be useful in the detection of gravitational waves. Thank you. In the detection of gravitational waves, this is going to be one of the big challenges for multi-messenger astronomy, how to use pulsars for detecting gravitational waves. And also one of the important characteristics of pulsars is just like we humans age, we all get older, we don't have the same type of energy as we had, say, 30, 40 years ago. Pulsars are also losing energy. And as a consequence of losing energy, the rotation rate sort of decreases and they spin down. Occasionally, you find pulsars when they get stimulated. For example, if you have a star quake, something like, just like you have earthquakes on the earth, you have star quakes in a star. If you have, for example, star quakes, then the pulsar frequency goes up. Normally, pulsar's frequency goes down. That is why you call it pulsar spin down. And now that you find that atomic clocks have become quite precise, they've been extremely useful in so many fields. In fact, they have been, instrumental in verifying so many important effects of relativity, both special as well as general. You find that pulsars have a big role to play in space navigation. And in that connection, GPS is probably one of the interesting connections you can make, how pulsars can be related to space navigation and the global positioning system. And I'll give a brief sort of overview of pulsar timing arrays after that. Okay, you'll be there. Okay. I have a graduate student, Qian Li, whom Professor Shantanu Basu and Shantanu Basu is a very fine, brilliant colleague of mine with whom I've been very fortunate to interact. He and we are co-supervising Qian Li. And Qian Li is working on some important aspects of gravitational waves. I'll briefly come to that. And this summer, I had a very good student from IIT Hyderabad. Therefore, this student came in on the MITAX Global Link Exchange. These are summer research internships for 12 weeks. And this year, Varenya came to work with me, and he was very good. And I'll discuss a little bit of the work that he has done, including some very important calculations on pulsar spin down. I had also a Chinese student who was also previously a MITAX intern from China. And he did very good work with me. We had a very good paper on pulsar spin down about 5 years ago in classical quantum gravity. After COVID, he went back to China, but he's planning to come back again and finish his master's, which is rather long overdue. Let's have a quick look at pulsars. What are pulsars? These are highly magnetized, fast rotating neutron stars. Neutron stars are stars where they're densely packed with neutrons. About 10⁵57 neutrons, I believe. Such a huge powerhouse of neutrons. They are so dense. And one of the great challenges, because of the very high density that they have, how do you find a relationship between pressure, density, and temperature for such objects? This is one of the really great challenges of astrophysics now. I may briefly allude to it as we go by in some of the later slides. Therefore, pulsars are highly magnetized, very strong magnetic field. They're fast rotating, and they emit radiation predominantly via magnetic dipole radiation in the form of jets. And as they rotate, you have the stream of radiation, it also rotates. It creates a cosmic lighthouse effect over the universe. Yeah. Therefore, this picture shows exactly how these beacons of light are rotating. This picture comes from the work of Michael Kramer, who is one of the great people in this field from Germany, from the Max Planck Institute. He has done great work on pulsars. Now, I say pulsars are the gem of general relativity. It is because of pulsars that the first indirect detection of gravitational waves was done. The first pulsar, CP means Cambridge Pulsar 1919, was detected by Jocelyn Bell in 1967. She was a graduate student then, very bright graduate student. And she observed periodic radio signals at the same declination and right ascension. These are the angles like co-latitude and longitude, which in the case of the this one. Yeah. Therefore, here in 1967, she was working and observed these signals coming in at the same declination and right ascension. He was a graduate student of Anthony Hewitt. But she discovered the pulsars. We have to give credit for the person who discovered it. And the credit goes to Jocelyn Bell. Of course, Hewitt was her supervisor. Hewitt got the Nobel Prize for this discovery. And of course, humans always learn, and Nobel Prize committees also keep learning. They realize they are made mistakes, and this is a learning process for the Nobel Prize committee too, that they did not give Bell a share of the Nobel Prize that was given to Anthony Hewitt. But anyway, that was to put a long story short. Bell later on got the Breakthrough Prize in Fundamental Physics in 2018. She came to our department in 2019, University of Western Ontario. She gave a very nice talk. And Taylor and Hulse, and Hulse was a graduate student of Taylor, and they discovered the first binary pulsar. This was in 1974, PSR 1913 plus 16. How the numbering and cataloging is done is a different way. The PSR stands, of course, for pulsar. And what they found was, they not only found the first binary pulsar system, but they found that this system was slowing down. And then they realized that this was happening because as the binary object, you have essentially two pulsars orbiting around each other. They were, because of the orbital energy that was happening, they were losing, the system was losing energy. And it was losing energy, and it was radiating this energy in the form of gravitational waves. And the orbital motion of the pulsar is causing the strong gravitational emissions. Now, it is to the credit of the Nobel Prize Committee that they gave both the supervisor and the student the Nobel Prize together, which is a very fair thing to do. Because Russell Hulse did a lot of work. Hulse was in Massachusetts, and Hulse was in Arecibo Observatory, Puerto Rico, and Taylor, his supervisor, was at Massachusetts. He used to come once every month or every few weeks to come and monitor all the work that was going on. And Hulse was noting these observations with a lot of patience. Therefore, one important thing we all learn, we all have to learn to be patient. Only when we are patient, we find that sometimes you see things which you could have missed. And this is, in fact, a big lesson for everyone, how patiently Hulse was tracking all these pulses. And suddenly he found there was a change in the timing. And then he realized, he called his supervisor, and basically Taylor came essentially running. He took the next flight, came to Arecibo, and then they realized that they have found a very interesting, great discovery. And that was the indirect detection of gravitational waves. And Bellew and Hulse, they're both PhD students during their discovery. Therefore, this is a picture of Joseph Taylor and Russell Hulse. Actually, I had the good fortune of meeting Russell Hulse at an APS conference once, soon after he got his Nobel Prize. He's a very pleasant person, very nice to talk to. And he told me that he was doing a second PhD in plasma physics, in fusion research at the Princeton tokamak. Therefore, that is what at that time he was doing. Now, pulsars, there are over 3,000 pulsars discovered now, and there are many more pulsars sort of hiding. And one of the important things is to find more and more pulsars and to see if you can make a map of these pulsars. This is one of the most important studies that could be done, to make a sky map of pulsars. Some of you people are may like this field, and you may have enthusiasm in pursuing these type of topics. One of the things you could really learn to, you could try to work on is on trying to make a sky map of pulsars, their location, discovering new pulsars, where exactly they are located, and whether they are potential sources of gravitational waves. These are some of the things that could be objects of further study. And you also have X-ray pulsars, which are accretion powered. That is, matter falls into them, infalling matter falls into them, and because of that, they gain mass and energy because of that. And they have a variety of spin behaviors and rotation periods. And they can spin either down or up over time. They spin up if they get a lot of energy, and then the frequency becomes higher. Therefore, that is how you get the spin up. You also have these very interesting objects called magnetars. Magnetars are very strong magnetic fields of the order of more than 10 raised to 14 Gauss, could be even higher, 10 raised to 15 or 10 raised to 16 Gauss. A normal pulsar would have about 10 raised to 13 Gauss. Magnetars have even stronger magnetic fields. And yeah, they are about 1,000 times stronger than that of a neutron star, which is about 10 raised to 13 Gauss. And you have this millisecond pulsar. As the very name suggests, you have milliseconds, that means 10 raised to -3 seconds. Therefore, you have pulsars with periods less than 10 milliseconds, and they are detected in radio and X-ray and gamma ray bands. And they're theorized to be originated from old pulsars that are sped up due to the accretion of matter. When infalling matter comes, these pulsars gain energy, and that way they speed up. They acquire energy and hence speed. And they're also called as recycled pulsars. And the millisecond pulsars are used extensively in pulsar timing arrays in the detection of gravitational waves. Now I'll give you a short account of gravitational waves. What are gravitational waves? Let us take a very simple example. Suppose I throw a stone into a pond. Then you find ripples originating, they spread out. Therefore, what is the analog in the situation of gravitational waves? Here, it is space-time itself that oscillates, that vibrates. And why does it vibrate? When you have very strong, highly massive accelerating objects going around, because of the acceleration, they are able to emit gravitational waves. That means there is energy involved in it. And how they emit gravitational waves is through the process called quadrupole emission. You have monopole, means it is like 1 over r type of term that you get. You have then the dipole, which is 1 over r cube. Then you have the quadrupole that comes in. And then you have the octopole, the hexapole, etc. Okay, therefore different powers of r in the denominator. And if you have a quadrupole type of situation, as the very name suggests, you have quadrupole, it vibrates like so and like so, to mutually orthogonal direction. And if you look at the weak field solutions of Einstein's equation, therefore when I say weak, that means you're thinking of the gravitational field being weak. That means even if you have a very strong source located, if you go far away from the source, then the gravitational field weakens over distance. Therefore, if you look at the weak field solutions of Einstein's equations, then the curvature terms become small. And if you then look at it, they exactly look like what you have for electromagnetic waves. For electromagnetic waves, this is how they look like. On the right-hand side, you have a source term. Here, the source term is the energy momentum tensor of the gravitational field. And h bar mu nu is the gravitational field, the amplitude of the gravitational field. Therefore, t is time, and del squared is the Laplacian operator, that is the second derivatives with respect to x, y, and z coordinates. Therefore, that is how you have the wave equation analog for gravitational waves. Whereas in the case of the electromagnetic waves, you have J mu, where you have charge density and the current density. Here, the analog is you have a tensor here. There are 10 components because of symmetry, and that is T mu nu. Therefore, the first indirect detection came from the Hulse-Taylor binary pulsar. And therefore, in 1915, actually, Einstein predicted the existence of gravitational waves. And he did it right. He predicted it in a very correct way. And he said, the solution is there, gravitational waves exist. And then he took a simple example, a double star, and then calculated the amount of gravitational radiation emitted from a double star. It was very small. And of course, he was right. He said the radiation has a negligible practical effect. Of course, in German, the language that he knew very well and he was fond of, there the effect of those words is much more strong than when I say negligible practical effect. He really meant to say that it was. Yeah. But therefore, he rightly concluded then. And later he had misgivings about his own discovery. And he was sort of, in a way, misled by his close collaborator, Rosen. And they wrote a paper saying gravitational waves do not exist. This was more than 20 years after this, in fact, 22 years. And then there was a referee from Caltech who rightly pointed out, you're wrong. He, of course, he knew Einstein by the time got a Nobel Prize. Of course, he was very sort of cordial, very thorough, but he gave a 4-page report in the physical review saying that he wanted this paper to be published. He didn't want to discard the paper, but he said, please take care of these suggestions that I'm putting in. And Einstein was one of those rare instances where he lost his cool. He said, we sent our paper for publication not to be criticized by an anonymous reviewer. And then he said, we will try to publish it elsewhere. And after 2 years, Leopold Infeld, another great relativist, succeeded in convincing him at Princeton that there was a mistake he did. And then he retracted immediately, graciously acknowledged it. And therefore, that is how there's a big history behind it. Therefore, 1915 was when Einstein correctly predicted the existence of gravitational waves. And it took 100 years to make the first direct detection of gravitational waves, 2015. But it wasn't announced until 2016, February. In fact, I was asking, there came one major colonel from the US Air Force who came to give a talk in February 2016 to our Space and Astronomy Center. That was on a Friday evening. I liked the talk very much. Later, I had a chance to talk to the speaker who was very friendly. I asked him, when do you think they're going to make the first detection of gravitational waves? I just asked him spontaneously. He did not give a talk on gravitational waves that day. He gave a talk on the Kepler mission and the advanced Kepler mission, etc. I asked him, he said, look, you'll know next week. I was surprised. He said, you'll know next week. Then I thought, that's fine. Therefore, that was Friday evening. On Tuesday morning, I woke up. Then after some time, I turned my iPhone on, wanted to see if I had any email messages. And my secretary at physics department then forwarded me an email. She said, your student has been in the LIGO discovery team. Therefore, that actually is still in the Western discovery site. The Western graduate on the LIGO discovery team. His name is Mark Normandin. He did his master's thesis with him. And then I referred him to my close collaborator and friend, Soumya Mohanty at Texas. He did his PhD at the University of Texas. And now he's doing neuroscience, but he was one of the people who shared the breakthrough prize for the discovery of gravitational waves. Therefore, you never know, anything could happen. Yeah. Therefore, this was true. Therefore, 2016 was when they made the actual discovery. Though they actually discovered it in 2015, they didn't want to make a rash announcement because they realized that if they make a small mistake, it will be all over the world. They didn't want to announce anything premature. Therefore, they checked and rechecked. And in September, they found in 2015 the direct evidence for gravitational waves, but they did not announce it until they checked and rechecked everything in February 2016. Okay, and now this year, in June 2023, you find that various groups of the Indian pulsar timing array, they reported the first evidence for a background hum of gravitational waves. Is this off or? Okay, it doesn't matter. This is from the static background, from the stochastic background of gravitation. There's a huge amount of stochastic background of gravitational waves. It is, when you look at it from a cosmic scale, the intensity is very small. Therefore, the point then is, if you have bodies either with or without mass, if they move in a curved space-time. And if you have, for example, very strong curvature, you find that all the geometry is encoded in the metric tensor. In the case of electromagnetic waves, you have the field tensor S mu nu. In the case of gravitational waves, it is in the metric tensor G mu nu. And G mu nu has, in principle, 16 components, but because of symmetry, 6 components sort of get reduced, and you have 10 essential components. And therefore, to find the distances, ds squared in space-time, you have the product of G mu nu, which is the tensor dx mu dx nu. Therefore, mu and nu run from indices 1 to 4. Therefore, you have, for example, G1 0 dx1 dx0, similarly G1 1 dx1 dx1, that means dx1 squared, etc. Therefore, you have 16 components if you have this, and you're multiplying these with each of these. Therefore, that is how you do that. But if you diagonalize everything, it comes in a much more tractable form. Therefore, you see that Einstein's equations are highly nonlinear. And only when curvature is small, then you begin to realize that you get simpler situations where you can actually work out solutions. And actually, there are some very remarkable Indian physicists by the name like Vishweshwara and Datta and so many others who have made Madhika, Vaidya, and so many others, very illustrious Indian relativists who have made so many monumental contributions in this field of general relativity. Now, of course, some of the work they have done many, many years ago is now being recognized. Therefore, Einstein's equations, if you look at it in a very simple-minded way, in a nutshell, you have the tensor G mu nu, which is essentially a function of the variables G mu nu. These are the variables for the metric tensor. And that is proportional to the gravitational constant. In the denominator, c is the speed of light, and T mu nu is the energy momentum tensor of gravitation. Therefore, it looks simple in principle, but when you really go to the actual nuts and bolts, it's a hell of a lot of work. Therefore, people have been working on Einstein's equations for, in fact, so many years, about more than 100 years, And always, people sometimes find very interesting solutions. And there'll be more coming in, you never know. And if you look at it in a very simplified way, when you think of your curved space-time becoming less curved and approaching flat space-time, which is called Minkowski space-time, then your G mu nu simplifies less. Yeah. G mu nu is the metric tensor. T mu nu is the energy momentum tensor of the gravitational field. It has 16 components. But if you have symmetry, it reduces to 10 components. Because you have a 4 by 4 matrix, if you have A12 equal to A21, for example, then you only count 1. Similarly, A13 equal to A31, you again count only ones, etc. That's why the 16 becomes 10. Okay, yeah. Therefore, how do you detect these gravitational waves? It is because of the tidal effects. We all know how tides are caused. Exactly, that's exactly the way the tides are caused. When you have the moon and the earth sort of going at different distances, and they vary, the distance changes, and they're orbiting around each other, you find that they have the high tides and the low tides depending on how near or how far they are. And that is how the tidal force comes in. And it is because of the tidal forces, which vary as 1 over RQ, that one is able to detect gravitational waves. And the strain that you induce is proportional to the gradient of the tidal force. Therefore, the gradient of the tidal force is del of del, that means 2 gradients. And that is how you get the 1 over RQ. For special situations, you can reduce it like 1 over R, and the 1 over R squared becomes like 1 over lambda squared, where lambda is the wavelength of the wave. Therefore, whenever you have binary systems which have a lot of orbital energy, they radiate gravitational waves, and they slow down. And black hole binaries emit gravitational waves during their in-spiral, merger, and ring down phases. I'll show you a picture soon. And you have the first detection of GWs was when LIGO detected a signal from the merger of 2 such black holes. And pulsars also emit gravitational radiation due to their high rotation speeds and asymmetries on the surface. You need a hill on the surface to be able to, because of the asymmetry, you get the emission of gravitational waves. If it is perfectly symmetric, it will not radiate any gravitational waves. This is a very important theorem. And you also have supernovae, where if you have very strong bursts, then you can also generate gravitational waves. Therefore, this is how the merger looks like. You have the in-spiral. This is the last stable circular orbit. You have 2 masses going around each other. These are black holes. They spiral around. And as they become closer and closer together, they are still at the last stable circular orbit. Then they slowly begin to merge. And once they merge, then they sort of become one object together. And it's the total mass here. The total mass is not exactly m1 plus m2. Some of the energy now gets radiated away. This is how the waveform looks like. The h is the gravitational wave amplitude as a function of time. And this is called the ring down. Hawking radiation is different. That comes from black holes. That is a different thing. That is also a very important idea, but it's not exactly the same as this. Yeah, it is somewhat different. Yeah. This is experimentally verified. Yeah, this is experimentally verified. I'm actually showing you the next couple of slides. Therefore, this is how they actually found the observationally verified that gravitational waves have been detected. And this is how it looks like. Therefore, as you can see, it's a lot of combination of analytical mathematics, numerical mathematics, and of course, a lot of sound physical intuition. You need all of these. And computers, of course, become very important in numerical relativity. Therefore, it's a whole interplay between so many talents of people. You realize in anything in life, particularly in science, you realize that everyone's work is important. Nobody's work is insignificant. Every work is important. Okay. Yes, please. Last stable circular orbit. Yeah. Okay. And this part of the wave was calculated from using the Troikovsky formalism. Troikovsky was a student of Kip Thorne, and he is originally from South Africa. He worked at Caltech for quite some time, and later he was at Cornell University, Ithaca. Yeah. Therefore, how exactly are these when you have the merger of these black holes, just like the chirping of birds, when you see birds chirp, you see the range of frequencies is quite high sometimes. You have the chirps. Similarly, when you have these objects merging together, you have chirps of gravitational waves. One of the important things that comes in is the chirps gravitational wave signal. And my student Q1 is working on the fast chirp transform. How exactly you can use the mathematics of the chirp sphere to be able to find, to detect gravitational waves and to see whether the chirp transform could be more useful in being able to detect gravitational waves compared to the fast Fourier transform. Everything is important. Question is, this is a very interesting topic worth study. And LIGO, when they first detected these waves, they also used a very good algorithm based on the chirp transform. There's more to it, and this is what my student is working on. If you look at this picture here, you have an n term, which is similar to a discrete Fourier series. And you also have an n squared term here. There you have the squared term. That n squared term that comes in, you find that that happens for a class of functions known as theta functions. These were originally done by Jacobi. I'll point that out. Yeah, these are the Jacobi theta functions. And if you look at it, you can rewrite this in this particular form in terms of cosines. Q raised to n squared cosine of 2nz. Okay, therefore, if people are more mathematically inclined, you can look at the book of Whittaker and Watson, for example, which gives a very good discussion of classical theta functions. But this was a little bit of work that my student did. He didn't continue much further on it, but he looked at this problem a little in detail, and you see these very nice pictures that come in for the Jacobi theta functions. Pardon? What are those images? Yeah, those are the pictures that when you plot these, this is how it looks like. These pictures are showing your classical theta functions. The theta functions, these are the theta functions. When you plot them in, because they have such a rich structure, it will be nice to show them in color. And these are multi-valued functions. You have periods, multiples of 2 pi, etc. That's why when you look at everything together, this is how some of those images look like. Go to the Wikipedia. If you go to the Wikipedia and look at Jacobi theta functions, you'll see many such images like that. Therefore, to go back to the earlier question of Hurst-Taylor, this is how they observed the slowing down of the binary pulsar, and the orbits are coming slightly close to each other. For every orbit done, it spirals in by 3 millimeters. And general relativity predictions and observations, they match with almost close to 100% accuracy. Therefore, this was, and this plot is from the work of Taylor and Weisberg. And the LIGO detection 2016, this is how it was done. Therefore, this is how the picture comes in, and one can study this in detail a bit more by using the fast chirp transform. Therefore, these are the two detectors of LIGO, one in Hanford, Washington State, and this is in the state of Louisiana, Livingston Observatory. And the source was between 230 megaparsecs and 570 megaparsecs. Parsec is 3 into 10 raised to 18 centimeters. Mega means multiply by 10 raised to 6, 10 raised to 24 centimeters. And you have 502 anywhere to 200, therefore it will be 200 times 3, say 600, and times again 10 raised to 24 and multiply by 100. Yeah, therefore it is pretty large distance, quite far away from our Earth. Amazing, amazing. Yeah, exactly. And some of you, yeah, incredible. Some of you, I know, you have very good experimental skills and background. I encourage people to take a spectrum of these studies, not just only one thing, because everything, as I said, is important. You need very good experimental people, very good computationally oriented people, very analytically oriented people. It is all together, they pull up a good piece of work. It's not just one side alone. And as Professor Deshmukh is saying, it's a fantastic interplay of skills of so many people and from so many different parts of the world. Therefore, this is the nanograph which was observed this year in June, and this is how they were able to find the gravitational hum. And both the Indian pulsar timing array and the European pulsar timing array, they worked on this together, and they had a good collaboration, and they were able to find this gravitational wave background. Now I'll come to the topic of pulsar spin down. Do I have another half an hour? Okay. Therefore, as I said, pulsars lose their rotational energy through various mechanisms. The most dominant is magnetic dipole radiation. Besides, they lose energy due to particle ejection, mass accelerations, gravitational wave emission, and higher order electromagnetic emission. And if you study the spin down, it helps model the rotational frequencies and periods of pulsars. Therefore, this is how you find that the frequency rate df by dt, which is your f dot. And as I said, pulsar is spinning down. That's why if it is spinning down, these coefficients f, r, g, and l are positive. Whereas if it spins up, some of these coefficients could be negative, and negative times the negative will be a positive. Now, if you ask me the question, how this came about, this is a very interesting model. And one of the things I wanted to point out is this. Sometimes when you send papers to journals, if you're lucky enough, sometimes you will find remarkably excellent reviewers. I first made a simple-minded attempt to study pulsar spin down in about 17 years ago, roughly about 17 years ago. There I had a paper on analytic study of pulsars, including Jovian corrections, because effects due to Jupiter, because Jupiter is going to play a role in affecting the signal, and Jupiter and the moon is going to play a role, and the Earth's orbital eccentricity is going to play a role, because Earth is not circular, it is somewhat elliptical. Therefore, when you look at all these corrections, then the gravitational wave signal gets changed because of all these effects. Therefore, when I did this paper along with a couple of my colleagues, the referee was very good. He said the work should be published. He said it's good work. But he said, don't include the spin down. You have not done a good job with the spin down. I am very happy with the rest of your work, but reserve spin down for a later stage. And I encourage you all to study pulsar spin down. Therefore, that was one of the most memorable reviewer reports I received, that person encouraged us to pursue pulsar spin down and said that what we had at that moment was not really quality enough to be able to merit publishing, but he encouraged us to pursue that further. Therefore, in 2018, we developed the first preliminary model where we included the first 3 terms on the right hand. And we were able to get and we sent it to the same journal. And we, in fact, told the journal that it is because of one of the reviewers of this, we have made a big attempt. And they were nice. They sent it to 2 reviewers who were, again, very good. They said, the work is interesting, but we really want you to rewrite, make it much more thorough and do that. Therefore, after 2 sort of edits, then the 3rd edit, they were happy. And therefore, that is how the second set of reviewers, which was also equally good. And that is how the 2018 paper, from 2006 to 2018, you see it's a big, big gap. And now it's 2023, and that is where we included this particular term, the F raised to 7 term. And this is because I had the student Varenya from IIT Hyderabad, and I told him about this problem, and he had the enthusiasm to try it. He said, I would like to try it. Then, of course, he was at that moment, I had 3 this summer, 3 MITAC students, but he came in a few weeks earlier. That meant I had a bit more time to give to him. Therefore, I spent regularly a certain amount of time, and he picked it up very rapidly. And I showed him how to do some of these calculations. By the way, this is a nonlinear differential equation. And luckily, you can actually do an exact solution for this. Therefore, as you can see, these different terms are due to different processes. This is the monopole term, and this is the dipole, this is the quadrupole, and this is what is called the arc mode. Arc modes, they're also called Rossby waves, I think, that occur in the ocean. Therefore, these have been already known in oceanography, but now for neutron stars, these have become very important. The arc modes. And because of arc modes, you can also generate gravitational waves. Yes? Yeah. 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 The spin down is coming because they're radiating away energy. If they're radiating energy, they're losing energy. You're right, they're moving fast. You're right about that. They're moving very fast. But when they're moving so fast, what is happening is they're generating a lot of gravitational waves. The spin is not because when they're losing this energy, naturally the spin also, because it is because of the spin that they're having this energy. And when they're losing the energy, the spin will become a tiny bit smaller. Yeah. Yeah. If you are asking whether they can collide headlong, if you have a merger, I don't know whether spin will become 0 fully. That's an interesting question, whether the spin can become completely 0. I don't think so. At least from the equations, it doesn't look like, but certainly I will check that. This is a question worth checking again, whether spin can become, when you're saying spin becomes 0, you're essentially saying angular momentum is becoming zero. And I don't know whether the boundary conditions will allow the angular momentum to completely become zero. It's worth checking. Yeah, it's an interesting question. Yeah, I look into it. Yeah. Okay, and as I said, negative coefficients mean glitches and you have spin-ups, like for example in Stark waves. And this is how the energy rate equations looks like. Therefore, you see they're losing energy. And when they're losing energy, naturally, this means that the frequency part is changing. Frequency is getting smaller, as you'll see in the next round of slides. And because of that, when the frequency, unless you have a glitch, if you have a glitch, then this frequency can go up. Can happen sometimes. If you have Stark quakes or other processes happen. But when they are losing energy, the rate of change of frequency has to decrease. It will be decreased. That's what you mean when it's negative. Therefore, this is how the monopole, the dipole, and the quadrupole rates. Therefore, E dot means dE by dt. And because of the different mechanisms, you see the power of the frequency is different, angular frequency. And this is how you look like. If you take the derivative, you get I times omega dot. And if you rewrite this, this is how it looks like. Therefore, the point is that if your rotational is decreasing gradually, that means your F dot is going to decrease. Therefore, R modes are the fluid mode of oscillation in neutron stars. As I said, they have been firstly found in oceanography when you have water waves coming in. That's how, and they're also called Rossby waves, if I'm not mistaken. Therefore, for the gravitational waves, they really came into the picture in 1990s. And therefore, they were people were beginning to get talking about R modes. And restoring force here is the Coriolis force. And therefore, whenever you have R modes, that means they're generally unstable to gravitational wave emissions. And the frequency of these waves is related to the rotational frequency like so. L is the angular momentum. Therefore, you see, I'm not anyway putting in all the mathematics behind, but after you work out all the math, this is how it looks like. And what is the pattern for this? If you have a frame rotating with the star, then you have the speed in the retrograde motion will be minus omega r over m, which is written like so. And if you have this situation, you have a retrograde motion, whereas if you have an inertial frame and you have the star rotating, you have sigma I is proportional to omega, but with a different L dependence. And this is prograde motion. When these two conditions are happening, then you get what is called the CFS. It stands for Chandrasekhar-Friedman-Schutz instability. This is one of the most important instabilities for neutron stars. It goes back to Chandrasekhar, the famous astrophysicist. Therefore, if you have the prograde motion, you have the R modes rotate faster and you have emission, positive emission increases, whereas if you have retrograde motion, it decreases. And this is how the expressions are worked out. And if you look at the R modes, it's F raised to 7. Therefore, that will give a contribution, the fourth spin down coefficient. Therefore, I was teaching Varenya, who also asked me questions about the Lambert W function. And we spent a few hours one afternoon. I was showing him all the ways how one can try to manipulate the Lambert W function. And then he himself worked out this relationship after I showed him all the little things about the Lambert W. Therefore, this is a new interesting result that we have in terms of the Lambert W. Therefore, these are new results. Therefore, we have put all this in the archives last month. And maybe my students are busy, and Varenya has gone back to IIT Hyderabad, and I don't think he has momentarily time to focus. But my student Chiwan said he would like to follow up and see if we should send the paper to monthly notices of the Royal Astronomical Society. Therefore, you see, the results Varenya calculated is extremely close to the observed result. Therefore, pulsars are used in navigation systems too. And if you have interferometry, for example, you can improve the resolution even more, up to 25 nanorads. And in principle, what happens is you have a pulsar and you have a beam of light coming in. It's received here, and then it gets a de-dispersion, and you have a barycentric correction. And then you have the create the pulse profile, and then the time of arrival measurement, and how the phase shift is observed, and then the position velocity. Therefore, this is the basic idea of how the thing works here. And what exactly happens in a pulsar timing array? You find that you have pulse profiles of the pulsar that people have studied quite accurately. And once you have that, then you find that you know the arrival times of the signal from the pulsar. And the timing is accurate up to 10 nanoseconds. And that means the distance accuracy is 3 meters, I think. It says 30 meters, 3 meters. And if you have a pulsar timing array, what happens is you have a whole string of pulsars situated at different places on the globe. And you find that you have, from different pulsars, you get pulsar arrival times. And these correlated signatures are used to detect gravitational waves. Because if there's a slight difference from your normal arrival time, you know something is happening. Therefore, that is how they detect these low frequency gravitational. And essentially, this idea is you treat the solar system barycenter and the pulsar as 2 points, opposite end of an imaginary arm. And that acts like a reference clock. And if you have a gravitational wave perturbing the system, there will be a slight change in the arrival time. And this is the square kilometer array. They have the 2 largest radio telescopes arrays in the world, located in Australia and South Africa. And this is supposed to go live in 2028, in about 5 years or so. And it is expected to be 50 times more sensitive than current radio telescopes. And so many countries are part of this, including India. India is playing a leading role. And one of the people who is doing a lot of work in this is Dr. Hamsa Padmanabhan. She is the daughter of Professor Thanu Padmanabhan, who unfortunately recently passed away. He was one of the most brilliant relativists we had, Thanu Padmanabhan. Yeah, his daughter, she's very brilliant too. Yeah, this is Professor Kipton. He was very nice to invite me to Caltech, and he was also nice to allow me to take a picture of him. Besides a few other pictures, I also took a picture of him when he was in his office here. And he was at that time the Feynman Professor of Physics at Caltech. And he has been very encouraging to me, very nice and supportive in whatever little things he could do for me. And when I visited Caltech, I happened to stay directly across the house where Einstein lived when he came to Caltech in the 30s. General relativity was very unpopular among so many people, particularly in Germany at that time because of the Nazi era. And many people called it Jewish physics. Therefore, Einstein had a very rough time getting his theory accepted in Germany. A few Germans, of course, supported him. They knew that he was right. But many were against, particularly the political wing, which was very strong at that time. Therefore, he was looking for a new haven. And Princeton was one of the places which invited him. But earlier than that, it was Caltech. Richard Tolman, who wrote this great book on statistical mechanics. Tolman, he was the person instrumental in inviting Einstein to visit Caltech. And he was here for more than a year, probably almost 2 years. Therefore, Einstein lived in this house here. I happened to go inside the house and meet the landlady who was very nice and very hospitable. I spent more than an hour with her. And I also happened to be in an Einstein Papers project during the early 2000s, where they were transferring Einstein's papers to the Caltech archives. And these are some suggested readings on pulsars and spin down. You can have a look at these. And IIT Tirupati, I acknowledge because the IIT Tirupati has been very hospitable and very open and supportive of the work we are doing. And MyTax Global Link has been giving me good students on most of the years. And each student essentially they cover all the support. I don't need to do except give them the $250 registration. Besides that, I don't do. The other expenses are taken care of by MyTax. So it's a very good thing to have. And any one of you who is eligible, I strongly encourage you to apply for the MyTax projects. There is one on gravitational wave data mining that has been put in, and also on the Lambert W function, and also on the Eisen model. Therefore, I encourage you people to apply if you think that any of these topics interest you. Therefore, these are the exact solutions that Varenya and I, along with Q1, did. These are exact expressions. Yeah. Therefore, we did that for the R mode. So, yeah. Thank you. Yeah. Yeah. Yeah.
Space and time is not immediately water. So how do you understand space and time?
You can think of space-time as an elastic fluid. It is like a fluid. Of course, if you think of water, you can much more intuitively visualize water. But if you think of space-time, think of it as an elastic fluid. You have the same type of thing, just like an ordinary fluid would behave. Another simple example I can think of is, if you have been on a travel, if you've seen a trampoline net, if you stand, put your feet on the trampoline net and bounce back and forth, what is happening? You find that you begin to go up and down, etc. Therefore, what is really happening there? You find that the trampoline net, the curvature is sort of changing, and you begin to sort of vibrate. And in a simple-minded way, just like you have stone thrown into the pond. Similarly, a trampoline net. Same way you think of space-time being perturbed. They have interference as well as constructive as well as destructive interference. Both of them can happen, just like ordinary waves. Destructive interference, of course, you can. Constructive ones, you can. Destructive one, maybe indirectly, you may be able to find that it is destructive interference. Yes? But that's right. That's a very good question. Essentially, you're asking relationship between quantum mechanics and gravity. The answer is this is one of the most challenging questions that people are working on. Yeah. Yeah, the point is, if you have these particles producing gravitational waves, they could in principle be due to quantum phenomena, of course. That is one of the possibilities. One of the most interesting examples, and this I really came to know because this is part of my PhD thesis. Suppose I have a photon, it's a particle. Suppose I have a very strong magnetic field, for example, around a pulsar. Okay? Therefore, here is a pulsar. Therefore, I'm having a very strong electromagnetic field due to the pulsar, and that I represent by another photon. Now, what is happening? I have this photon interacting with the magnetic field of this pulsar. That means I have interaction of electromagnetic waves. That means there's an energy momentum due to the interaction of electromagnetic waves. Now, gravity couples to everything in the universe, to the energy momentum tensor of all fields. Therefore, what does it mean? I have the energy momentum tensor of the electromagnetic field, and gravity can automatically couple to it. Therefore, when I say gravity couples to this, what does it mean? It means that I have the generation, the gravity. This is the photon, this is the photon, and this is the graviton. That is the simplest Feynman diagram that one can think of for the interaction, as you said, of particles. And in this case, it's an electromagnetic field. You can also have an interaction with a gravitational field and also generate either photons or gravity. There are different processes possible. Actually, if you want to get a little bit of idea on this topic, my supervisor and myself, we have written a review article in Physics Reports. It's called Gravitons in Minkowski Spacetime. And it is in Physics Reports. There you will find many different processes, how you can generate gravitons. This is a simple article. If you find you may get something interesting out of it, go through it. It has a lot of good references. And you may be able to work on something that you like, following these things here. Yeah, my supervisor has also recently written another book here with another person from Italy. I don't remember the title, but if you look under Papini, then you'll also find that one. Yeah. That's a very good question. Yeah, very good question. If you go back, even 50 years ago, people thought that gravitational waves is just a topic for the ivory tower. Nobody thought it is useful. It was also very difficult to get grants for study of gravitational waves. Very difficult on the average. Okay. But recently what happened is, that is the beauty of it, human beings. Many of them don't stop working just because they're not given funding or things like that. Some human beings are very resilient. They don't give up so easily. And because there are enough such people, you find that the study has progressed. And Kip Thorne and Raina Weiss, these are the two people who really fought to get a big grant from the National Science Foundation. Therefore, that is how this project called LIGO, means Laser Interferometer Gravitational Observatory, was funded. It is because of these two giants who really did a lot. They didn't award it to the superconducting super collider at that time because that was even more expensive. They gave it to the gravitational wave, luckily won out. And with that, they really began to make a lot of progress. And the Europeans also, the Virgo project, they also did a lot of work. And then the UK team, Cardiff and Glasgow, and that in their smaller way, they also did a lot of contribution. And now, of course, Japan and other countries are also joining. And India is also, they have the Indigo, the Indian LIGO that has joined in. Therefore, if you're asking, what are the spin-offs? So many have come in. Interestingly enough, after people began to study the detection of gravitational waves, they had to learn so many different ways, as Professor Deshmukh was saying, to be able to have a technology which is so precise that they could measure things as small as 10 raised to minus 21 centimeters. It's mind-boggling. Therefore, you can understand how precise a technology you need for this. In the process of doing all this, they developed very high quality of superconductors, very high efficiency superfluids. They also developed very good magnet design. They also did great things in interferometer optics, Fabry-Perot and Michelson interferometer optics, also quantum optics, including things like squeeze states, etc. Because you see that they wanted to make the things much more cold, cryogenic sensitivity. That means they had to reduce the temperature. And in the process, some of the people are beginning to study also Bose-Einstein condensation. Therefore, you see how things are getting related from so many different fields into what you thought was completely isolated from the world. Yeah, people, a long time, they thought it was only the math department most of the time, general relativity. But now it's not only in math, but other departments. The philosophy department, there are quite a few philosophy departments in the world where they study general relativity very well. In fact, I taught at least 6 times general relativity from the philosophy department. Physics department supported later, not in the beginning. It was philosophy department which gave me a chance, me and my colleague Bill Harper, to give the first course on Newton's Principia and then general relativity. Yeah. Yeah, I think it could, of course. You could have lensing, gravitational wave lensing. Yes, it could. Yeah. Yeah. Good. Nice. Good. Definitely, it's a very good question, and certainly it's going to affect. Actually, there are people who really know much more on this than me. One of them is Priyambada Natarajan. She's at Yale University. There are few people in the world who have done a lot of studies on dark matter. If you look up Google or Wikipedia, you may dig up names. And most of these people, if you write to them, generally they are helpful. You should explore it further. This is a very good topic, by the way. What is it? Oh yeah, of course. Yeah, you have the gravitational wave is the wave aspect. The graviton is the particle aspect. Graviton is the quantum of the gravitational wave. It's a wave, but if you're asking, does it have a particle aspect? Yes. It is also a wave. That is the wave particle. Yes, it has a mass, very small mass, almost zero, but it has a mass, almost zero. Almost zero. You can actually set precision limits for the mass of the graviton.
Great talk, Ram.
Thank you. Yeah.
Such fundamental topics. The good thing is that all of you have an opportunity to get answers from them. Professor Valluri is very closely associated with us. As I mentioned, he has already mentored 7-8 students over here. Actually published papers with our students of IIT Tirupati. He will be here for another few days. He's here till Monday, Tuesday morning
Yeah.
actually.
Yeah. Sunday evening I'm back, but Monday I'm available.
Please send him an email or send me. I'm happy to enable your interaction. We will, I think, close the session. It is close the session only for now. But I think the interactions will continue. There is no way we can thank you, Ram.
Oh, thank you.
I don't even want to do that.
Thank you.
It's impossible for me to do that. So I don't want to be the step. The only way to thank you is to take full advantage of your interaction with the students.
Thank you.
And I'm sure that the students will benefit from it. So we will meet some other time. But before we depart, can we all assemble here in the picture? You have a picture, everybody. You also should be the picture. Oh, is it right? Sure, everybody. I can get a picture. No problem. Yeah, yeah. So let's come into the picture, everybody. All of you. Please join us. Yours,